So as Dan said, tonight I'm here to talk to you about Boxcar, our self-balancing distributed services protocol. And I'm RB Boyer. I'm a software engineer on the resume team, and I help people get jobs. And the way I do this is by solving interesting problems. One of the cool parts about working at Indeed is that by solving these interesting problems, I get to affect the lives of millions of job seekers around the world, which is pretty rewarding. Boxcar was the solution to one such problem, perhaps the most fundamental problem. How do we build Indeed itself? Normally, when we build new products, we follow 4 key guiding principles. We like to keep things simple, fast, comprehensive, and relevant. But when we're building the fundamental architecture of the site itself, we're not so much building a product as we're building a system. And when we build a systems at Indeed, we follow 4 other guiding principles. We still like to keep things simple and fast, but we also want them to be resilient and scalable. I want my application to be more complicated, said no one ever. Complex things create confusion, and confused individuals write bugs. By keeping our system simple, we limit the number of bugs that are introduced. I want my application to be slower. Google conducted a speed test, and in this test, they added 500 milliseconds of latency for every search. And in the test group, what they found was that there were 20% fewer searches. Speed is a feature, and our users notice it. They expect it. I want my users to experience outages. It's a fact of life that programs will crash, machines will die, and we have to be ready for this. We have to write our systems so that when these failures inevitably do happen, they'll survive. My system will only need to support 10 users. We want to be able to scale our systems by adding more machines, not bigger machines, because bigger machines are expensive machines. For those of you that don't know anything about Indeed, here's the quick summary. This is a search results page. There are 2 boxes at the top. One is the what, and one is the where. In the what box, you enter your search query, like Java, and in the where box, you enter where you're looking for that job. And when you press the Find Jobs button, we show you a list of jobs that match the query, Java jobs in Austin. To the average job seeker, this is deceptively simple, and deliberately so. To them, Indeed is a big black box that does magic for them. We go out and crawl all the job sites in the world and present these jobs in an easy-to-use fashion for them. Behind the scenes, this problem decomposes into 2 main subproblems. Aggregation is in charge of going out and crawling the internet looking for jobs, and job search takes the jobs found by aggregation, makes them searchable, and exposes them to users. Each of these 2 subproblems decomposes further and further into smaller and smaller subproblems, all cooperating together to build what we call Indeed. So our challenge as we grow is to keep this simple, fast, resilient, and scalable. So how do we do this? One way, we could have all these individual components sharing direct access to some data. For example, let's consider a shared database. Many projects begin with a single shared database where you stuff all of your tables. Many projects also begin with a single web app talking just to that database. Inevitably, someone asks, hey, can you build this thing for me? And you sigh, and you point it directly at the database to get the job done in a hurry. There's nothing wrong with this. Someone else comes to you and says, hey, can you build this other application that needs access to similar data? You point it at the same database to get the job done. Again, there's nothing wrong with this. And then you hire an intern, and another intern, and so on and so forth. And at some part, you start to ask yourself, hey, what is using my database now? This is an anti-pattern. And if you continue this trend on a long enough timeline, what you end up with is a maintenance nightmare, where you have no idea what's talking to what or why, or what will fail if you change something, like dropping a column or adding a new column. You're paralyzed and you can't make changes without fear of breaking something. So sharing direct access to the data is out. That only leads to paralysis and sadness. So what else can we try? We could insulate the data from the consumers that need it. Take our example from earlier. Instead of having all the applications directly talk to the database, we could shield that database and introduce a service in between them. All of the applications instead talk directly to the service, and the service is the only thing that talks to the database. But what's a service? A service is just another application, and clients talk directly to it over the network. And the service is in charge of all of the icky technical stuff required to implement all of the things that the clients want to do. Things like talking to databases, interoperating with caches, and all of the weird business logic that changes week to week. The important thing here is that the clients only have to care about a simple, easy-to-use API, and all of the other stuff is handled by the service. One such easy-to-use API might look like this, a get jobs method, and the only thing the client has to do is pass a list of job IDs. On the other end of the wire, the service might choose to implement it like this, with this medium icky SQL query. The important part here is that the clients don't also have to implement this query. They can be completely ignorant to this. If you continue this pattern of building applications on top of services, what you build is a service-oriented architecture. And at Indeed, we heart service-oriented architecture. One such example is the job search web app that powers www.indeed.com. This is composed of over a dozen different services, some of which are listed here. And how do we build services at Indeed? Boxcar. Boxcar is a self-balancing, distributed services protocol. And like most superheroes, it has a tortured origin story. There was a life before Boxcar at Indeed. And there were services in use before Boxcar at Indeed. So to keep things grounded, I'm going to focus on one such service tonight, the doc service. If you'd like to know more about the doc service, we devoted an entire previous tech talk to it. But the short summary is that doc service is in charge of controlling access to jobs. The main job search web app needs these jobs and uses doc service to retrieve them, which in turn retrieves these jobs from the doc store, which is the data structure we've built. So how do we put these pieces together and build this small snippet of our architecture? Well, we start simple. We need a web app. And in order to make it work, we need to give it access to a doc service so that it can retrieve jobs. And then we wired it up to the internet. Now job seekers can search the website, so mission accomplished. But how do we know that this is the best possible configuration? And is it good enough for us? To figure this out, we can go back to our original 4 guiding principles of keeping things simple, fast, resilient, and scalable. And from these, we can derive a goodness metric. We want our deploys to be simple. We want to make efficient use of our network so that requests are fast. We want our systems to be resilient in the face of failure. And we want to scale our systems horizontally by adding more machines, not vertically by adding bigger machines. So how does this lone silo stack up against our metric? You can imagine if any one of these components were to fail, all requests to the site would also fail. So this is not a very resilient configuration. So let's add more resilience. The simple thing would be to just add another copy. But now we have to figure out which stack to send requests to. So we introduce a load balancer. When we select a load balancer, we can choose a hardware solution like a NetScaler or a software solution like HA proxy or ModJK. In this case, each web app is only talking to one service, and there's no cross-machine communication going on. So you can imagine these are all silos. So we can call this configuration a siloed stack approach. How does this compare against our metric? Well, every machine is exactly identical, so our deploys are fairly simple. All client web apps talk directly to one service, so we're using our network efficiently. And if any one machine were to fail, the load balancer will simply route traffic around it. So the system is resilient. But is it scalable? Say our monitoring metrics tell us that the web apps are becoming overloaded and we need to add more capacity. Ideally, we'd like to add one more web app to process some of the load. But unfortunately, due to the way that silos work, you're going to need to add one of everything else. And for a simple configuration like this, it might be fine. But as you add more and more clients and servers to your system, it's going to be harder and harder to squeeze all this stuff onto a single machine. And you're going to need to buy bigger and bigger machines. This is vertical scaling, not horizontal scaling. We did, however, use the siloed stacks approach to implement some services for a period of time. But we knew that we could do better. One way is that we could improve the scalability of this configuration. And to do that, we could introduce a load balancer between the web apps and the doc servers. Now, we're free to add as many web apps as we need to service that load, and we can add doc servers whenever we feel like it, and we don't have to keep them in a one-to-one configuration. Each service that we implement has to have its own load balancer, so we can name this configuration the per-service balancer approach. How does this stack up against our metric? Well, now we've implemented another moving part in our system, the back-end load balancer. That's another piece that our operations team has to configure, deploy, and monitor. So the deploys aren't quite as simple anymore. We're free to add as many machines as we need wherever we need them, so it's horizontally scalable. But is it efficient, and is it resilient? Passing all of your front-end requests through a load balancer to the back-end service results in twice the bandwidth on your network. And this isn't very efficient. And from a resilience standpoint, the back-end load balancer represents a giant flashing red single point of failure in your architecture. If the load balancer were to fail, all requests to the site would also fail. So clearly, we need two of them. And then we need to balance them somehow. But luckily, this is a solved problem. You can have your two balancers set up in a master-slave approach where they share an IP address, and there's a heartbeat between them. When the slave detects that the master has gone away, it can assume mastership and resume balancing your load. Now, obviously, this is a more complicated approach, but in the name of resilience, it's necessary. So now the system is resilient. But some of you may be asking yourselves, hey, can't the front-end load balancer also fail? And indeed it can. And that's best explained in a previous tech talk, redundant array of inexpensive data centers. So the per-service balancer approach was resilient. We ended up using this in production for some services for a while, and it worked relatively well. But we knew we could do better. One way is that we could improve on the network waste. If we take the per-service balancer approach, we could simply dissolve the back-end load balancer completely and have each web app talk directly to each back-end doc server, doing a naive round robin between them, sending 50% of the requests to the doc server on the left and 50% of the requests to the doc server on the right. Now, we no longer have the extra moving part, so our deploys are simple again. And nothing has changed on the scalability front. But is it efficient with the network, and is it resilient? Well, all of the connections from the web app to the doc service are direct, so that network is being used efficiently. And from a resilience standpoint, you could imagine if you had two servers and one of them were to crash, the front ends are still going to send 50% of the requests to the left failed server. And because the server's down, it's obviously going to fail. One way we can introduce resilience into the system is to have clients simply retry failed requests on the next server in the round-robin pool, where hopefully it will succeed. So we can make naive round-robin resilient as well. It passes all of our tests. We should have used it in production. But there's one thing we're missing. In previous configurations, we've relied on the load balancer to take care of all of our load balancing for us with all of the magic pixie dust it owns. But since we've dissolved it and rolled our own solution, we have to prove that it's also balanced. So let's consider a situation where we have two servers and one is slower than the other one. The slow server will be on the left and the fast server will be on the right. Half of the requests are going to go to each server, but the fast server will be able to keep up with the incoming request rate, whereas on the slow server, the requests will stack up higher and higher, and at some point, that slow server is either going to run out of RAM and crash, or will simply start rejecting requests. This is not balanced. One of our machines is completely overloaded, and that's not cool. We knew this was a problem. We never used this in production. But it was so close to being our holy grail. If only we can fix the balancing problem. So let's take another stab at it. We go back to the per-service balancer approach, and instead of dissolving the load balancer completely, we break it up in little pieces and give each client web app its own mini balancer that it consults to figure out which server to send requests to. This configuration is Boxcar. It's somewhere on the spectrum between the naive round-robin approach and the per-service balance approach from earlier. And the logic inside of that mini balancer is really simple. The gist is that servers assign a numeric value to all incoming connections, and clients will always use the connection with the lowest numeric value to service each request. In Boxcar, servers only aspire to be the best possible server they can be. And to do that, we give them a relatively simple task. They have to keep track of an ordered list of connection slots. These slot numbers are just that. They're just numbers. There's an ever-growing number of them, and a server will never run out. They do not represent a priority, and they do not affect the way that requests are processed. They're only an implementation detail of balancing. And low slot numbers are the best slot numbers. This applies to both the clients and the servers. When a new client request is made to a server, the server consults its list of slots to figure out the lowest slot number that is not allocated. In this case, 2, which it then uses to label that connection. Clients, on the other hand, aspire to be the best load balancer they can be. And to do that, they maintain a fixed size pool, which they fill with connections to servers. The clients are aware of the slot numbers that label these connections, and these connections are long-lived. They are used to process multiple requests over their lifetime. And clients are greedy. They only want the best connections, and they are never satisfied. They are continually on the hunt looking for better and better and better connections, and when they find them, they throw away their worst connections. This all happens in the background in each of the clients. They continually scan the list of servers that they're aware of, asking them for their best available slot numbers that they're ready to hand out. In this case, the greedy background thread may contact server B, which would hand back slot 17. The greedy background thread examines the pool, discovers that 17 is way better than 57, closes that connection, makes room in the pool, and keeps slot 17 open to server B. This process continues forever because that greedy background thread is never satisfied. When requests come into a client, the client consults its pool and finds the lowest idle slot to process that request. In this case, the get jobs request will use slot 12 because it was the lowest idle slot. It's important to note that connections are not established on demand, meaning that if a request comes in to a completely active pool where every connection is being used to process another request, that request will fail, meaning that it's imperative that the pool be sized appropriately for the amount of concurrency you expect at any point in time in the client. To summarize again, servers assign numeric value to incoming connections, and the clients always use the connection with the lowest numeric value to service each request. And what happens by everyone playing by these same rules is that the emergent behavior of the system is the load balancing that we seek. Some of your heads are probably spinning right now, So I'm going to use a very simple example to make this more concrete. Let's consider a case where we have 2 servers and a client. This client will have a pool of size 2. In practice, we would never use a pool of size 2. We use something between 16 and 48. But if I tried to do that on these slides, they would explode. The greedy background thread is always running, so it may contact server A. Server A has no allocated slots yet, so it hands back a 0. The client knows that 0 is better than nothing at all, so it keeps the 0. The greedy background thread continues contacting server B, which also hands back a 0, which it keeps. This process continues in the background indefinitely, but in this case, the greedy background thread is only ever going to find a pair of 1s, which are worse than the 0s it already has, so this system reaches a steady state. All of the background thread is happy, the pool is full, and all requests are being processed. So say we have some new clients join the party. Client Y joins with a pool of size 2 as well. It repeats the same process in its background thread, contacting both servers, finding a pair of 1s, and keeping them. It also continues scanning all of the servers in the pool looking for better connections, finding 2s, which are worse than the 1s it already has, so it discards them. And a third client joins, client Z. It repeats the same process, finding a pair of 2s, which it keeps, and it continues scanning the pool, finding only 3s, which it discards. The system reaches a state of balance again. All of the background threads are happy, all of the pools are full, and all requests are being processed. Say something horrible happens, and a server blows up. All of the connections that were open to the clients are severed, and now all of the clients find themselves in a situation where they have half-empty pools. The greedy background threads continue like normal, scanning for better slots. In this case, client Z finds a 3, which it keeps. Client X finds a 4, which it keeps. And client Y finds a 5, which it keeps. This is the best possible configuration that these clients can find themselves in. So this system reaches steady state. Now it's important to note that these greedy background threads are not only contacting the live servers, but they're also trying to contact the dead servers, because they're eagerly anticipating the resurrection of that server so they can steal its best slots. So let's say some poor ops person gets woken up in the middle of the night, groggily figures out what's wrong with the server, and fixes it. Z contacts server B and scores the sweet 0 slot, which is better than the 3 it already had open, so it keeps the 0 and discards the 3. The pools are always sorted, so the client fixes that. Client Y also contacts the newly resurrected server, finding a 1, and 1 is better than 5, so it keeps the 1 and discards the 5. And X is last to find this out and contacts server B, finding a 2. 2 is better than 4, so it keeps the 2 and discards the 4. This is the best possible configuration these clients can find themselves in. So again, we reach a steady state of balance. All of the background threads are happy, all of the pools are full, and all requests are being processed. Say as part of our weekly rolling deploy cycle, we decide to shut down client Y to give it some new code. It gracefully closes all of its connections, relinquishing both 1 slots. Client Z contacts server B and finds that a 1 slot is available now, and a 1 is better than a 2, so it keeps the 1 and discards the 2. Client X does something similar, scoring the 1 slot from server A, which is better than its 2, so it keeps the 1 and discards the 2. This is the best possible configuration these clients can find themselves in. So again, we reach a steady state of balance. All of the background threads are happy, all of the pools are full, and all requests are being processed. Well, that rolling deploy took forever, but it's finally done. Client Y is restarted, and it has an empty pool. So like before, it fills it by contacting both servers, finding a pair of 2s, and keeping them. And this 2 is balanced. Now, I just showed you that Boxcar balances, but why? You can imagine connections are like running water seeking lower ground. And to visualize this, you can imagine servers as buckets, and the depth in these buckets represents the slot numbers it's willing to hand out. As connections are established across the pool, all of the 0 slots are claimed first, followed by the 1 slots, before moving on to the 2 slots. And what happens is that you end up with a roughly equal distribution of connections across your pool of servers. Unfortunately, this algorithm does have some unfortunate edge cases. From earlier, this configuration was said to be balanced, but something doesn't feel right about it. The problem here is that each client is talking to only one server, meaning that if one of the servers were to suddenly crash, one client will find itself with a completely empty pool. And because connections are not established on demand, this means that for a period of time, every request to that client will fail until the background thread gets a chance to replenish the pool. This is not resilient. One way we can fix this is by adding a touch of entropy to the system. We call this process table shaking. And the way it works is that servers only allow a client to use a connection for a fixed number of requests, say 1,000. And after those 1,000 requests are used up, the server will close the connection. Further attempts to use that connection to service a request will fail. And clients know that this happens, and they expect failure at any point in time. And when a request fails, they simply retry that request on a different connection until it succeeds. What this results in is that these bad configurations, though still possible, are far less likely overall. So though this particular configuration is still possible, this is the more likely long-term configuration, where if a single server were to crash, no client would have a completely empty pool. We can also exploit the slot number mechanics to do some neat tricks. One such trick is handicapping. Handicapping is server self-quarantine. Servers may have a list of dependencies, and at any given point in time, some of those dependencies may not be functional. A server with some failed dependencies is considered to be unhealthy. And if a server knows that it's unhealthy, it can exploit the way that slot numbers work and elevate its base slot number to some absurdly high value, like 1,000,000. And as we saw earlier, very high-valued slots are avoided by clients like they're the plague. So if we go back to our bucket analogy from earlier, and we imagine the 4th server suddenly became unhealthy, when it raised its base slot number, connections would redistribute to the healthier servers that have lower slot numbers. Now, if all of the servers were unhealthy at the same time, they would all raise their base slot numbers and all share the load. This is acceptable because even though a server is unhealthy, it doesn't mean it can't serve some requests. And we prefer that the site gracefully degrade rather than outright fail for users. So going back to our original metric that we used to evaluate these different configurations, is Boxcar any good? Well, there are no extra moving parts to deploy or configure, so the deploys are simple. All of the requests from the clients to the servers are direct, and it makes efficient use of our networking. You can add as many servers or clients as you need to handle your load, so it scales horizontally. But is it resilient, and is it balanced? Well, as we saw earlier, clients are always pessimistic, and they assume failure at any moment. And when failure happens, they'll simply retry those failed requests elsewhere. So Boxcar is resilient. But is it balanced? Some of you who are more astute may have noticed that we never actually balanced load in this presentation. We've merely balanced connections. Before I go on to explain how Boxcar balances load, it's helpful to review what we didn't like about the way that naive round-robin balanced load. So let's go back to our slow server, fast server approach. When the request came in, we found that the slow server slowly stacked up connections. This was the problem. This was the core problem with the naive round-robin approach, because when the connections stacked up, the server eventually crashed. But in Boxcar, there are a fixed number of connections, so there's nothing to pile up. Let's revisit our slow server, fast server example. And to make it easy, we're going to stick to a single client's view of the world. This client's going to have a pool of size 2. It's going to have a 7 slot open to the slow server on the left, and a 9 slot open to the fast server on the right. When a new request comes in, it will use the 7 slot because it always uses the lowest slot number it can find. So it sends that request to the slow server. When the next request comes in, it would like to use the 7 slot, but that's currently busy. So it has to use the 9 slot to the fast server. And because the fast server is fast, it processes that request quickly. When another request comes in, the 7 slot is still occupied on the slow server, so it too has to use the 9 slot on the fast server. Eventually, that 7 slot gets freed up, so when the next request comes in, it can go to the slow server again. And this process can repeat. And at the end of this, you see that the slow server has ended up processing fewer requests, and at no point did it become overloaded. This is what Boxcar gives us. Slow servers end up handling fewer requests, and no servers become overloaded, while at the same time, we still process every request. What we get is that the load balancing that we want is a probabilistic outcome. At any given point in time, the system may not be balanced, but over time, the system will be balanced. So, Boxcar is balanced, passes all of our tests, it gets our seal of approval. This is good enough for Indeed, which is a really high bar. Boxcar services well over 1 billion requests every day across our infrastructure. It's a fundamental piece of technology we use behind every aspect of the site. It powers over 20 different services, ranging from search engines to authentication systems. And we've been using it to keep the site operational since 2009. At Indeed, we heart Boxcar, and we love the service-oriented architecture it allows us to build.